In this lecture, we're going to talk about k-means clustering, continuing our discussion on clustering in general. Recall from last time, the first part of this module, we talked about 5 different learning objectives. First, looking at different kinds of machine learning, specifically 2 different kinds of machine learning, that is unsupervised learning and supervised learning, where in the clustering case, we're focused much more on the unsupervised learning case. That in machine learning in general, we have 2 different kinds of tasks. In the first kind of task, we have some data, and we want to extract or learn to identify some structure in this data. And we don't necessarily know what this structure might be beforehand. We might know what it means or have some idea of what we want to go for, but we don't necessarily know what this structure is. And in contrast, we want to learn something, or machine learning can learn something about relationships in a given set of example data, such that we can generalize these relationships. So when we see new data come in, we can predict or classify or infer something about these relationships on this new data based on relationships that we can extract from our existing old data. So this type where we're trying to extract some structure is generally referred to as unsupervised learning, where we don't know what that structure is beforehand. And on the right, when we talk about generalizing from examples of data, this is more about supervised learning, where we have some label, we have some examples of these relationships like labels, scores, etc., and we want to build a model that can help us recover or predict those relationships. So we talked about how we know whether one problem is supervised or unsupervised. In the unsupervised case, your goal is primarily to identify structure in your data, even if you don't necessarily have examples of what this structure might be. You might have examples of the full data, but you don't know how they are, you don't have good examples about how they cluster together or what the most important aspects of their underlying structure might be. But you want to have methods that help you find that. In contrast, in supervised learning, we do have examples of these known relationships. Our examples have a lot of feature information about what describes these examples, and we have some clear examples of the relationships, like labels or scores or something along those lines, and we want to build a model that helps us recover those existing labels. Now, really, this talks about whether you have labels for your data in supervised learning. Because in contrast, in unsupervised learning, you don't have labels. But labels can mean a bunch of different things. In the unsupervised case, we talked about 3 different kinds of tasks. The first is about extracting similar elements, or grouping similar elements together. That's the clustering case. Related to this is the idea of identifying dissimilar elements, or outlier detection, basically saying we have a bunch of data that all looks primarily this way. So when we identify new elements that are very far away from our current set of existing elements, these are somehow different or anomalous. So this is the outlier detection task. And also we have extracting latent structure, where we have a lot of data. We want to be able to reduce its dimensionality or find some lower dimensional structure or some embedded structure here, even if we don't necessarily have examples of what that structure may be. So when we talked about dimensionality reduction, this is primarily an instance of unsupervised learning. In supervised learning, there are 2 primary kinds, where we have, on the one hand, clear, discrete, categorical kinds of labels, and each of our example data points has some associated label or sets of labels. And what we want to do, the goal here is to classify our examples into these labels and build some model that helps us classify new unseen data into the same set of labels as well. In contrast, we also have what's called regression, where instead of having categorical labels around our examples, we have some numeric score where there is some idea of distance associated with these scores. And what we want to do here is predict scores based on these continuous values. So rather than predicting whether an element is in one class or another, or in a couple of different classes, in the regression case, we want to measure or evaluate whether we've extracted the score or numeric value associated with this example correctly. And we'll talk about supervised learning in a couple of modules. For now, though, we'll talk more about the clustering case. Having identified this context as being an unsupervised learning question, with clustering, what we want to do is identify similar groups in our data, where this similarity has some sort of realistic meaning, or is meaning that we care about. And we talked about a formal definition for clustering, say given a set of points and some metric for evaluating distance between them, Euclidean distance, cosine similarity, Mahalanobis distance, some sort of distance metric. With clustering, the objective is to take these points and group them into k clusters, where k is either some learned value or some pre-specified value. And we want to build these clusters such that points in the same cluster are much more likely to be similar to each other, whereas points in different clusters are much more likely to be dissimilar. So this is similar in concept to the community detection methods that we talked about in the network analysis piece, or network analysis module, where we talked about modularity and points in the same community, where nodes in the same community in the graph are more likely to be similar to each other than nodes in two different communities. So how might we actually build this clustering in a given space? So we talked about two different methods of doing this, using hierarchical learning and another kind of clustering called point assignment learning, or the point assignment method. In the last module, we focused more on hierarchical learning, where we have some data and we want to build some clusters that have some sort of hierarchical structure. And we talked about two methods for this. One is the agglomerative method, where we build these clusters from the bottom up, starting with all points existing in their isolated clusters, and then we combine clusters together in some clever way, or some understandable or driven way that makes these clusters better than other clusterings. And in contrast, you have the divisive hierarchical clustering, where we start with one large cluster and recursively split it up until we have a good clustering, or we have clustered all elements into individual points. On the other hand, like I said, we have the point assignment method, where rather than having a hierarchical structure here, the only information we have is a set of clusters and assignments about which points belong to those nearest clusters, which gives us some ability to do summarization, which we'll talk about. So here we have some set of points, and what we want to do is, given some new point, which one of these sets of points do they belong to? And there are associated questions here about, well, how many clusters do we have, and how do we represent these clusters? So in this point assignment method, this is really what k-means is, or k-means is one of the most popular examples of the point assignment method, which we'll talk about today. The next thing we talked about last week was about representing clusters of multiple points, the idea being that when we have multiple clusters, we need to evaluate similarity or distance between two clusters so we can identify which clusters we should merge. So how do we represent clusters of many points? Given that we have this cluster here at the bottom, what is the position of this cluster, and how can we compare it to the position of other clusters? In the Euclidean case, what we did is evaluate or identify or calculate the centroid of this cluster, which is essentially what point in space is the average of all of these other points in this particular cluster. And that point in space, that centroid, doesn't necessarily need to be a point in the actual data, but it is the average across all the points here. So what happens in a non-Euclidean case? Well, here we can't really talk about locations between points in the same way that we can in the Euclidean case, because in the Euclidean case you can draw lines between 2 points and put a midpoint between those 2 lines, and that's somehow the average of the average point between these two data points. In other cases, like cosine similarity, this starts to break down, because if you have 2 points, which are really 2 vectors in the cosine similarity case, what you're trying to evaluate is the angle between them. Well, what is the midpoint in the angle between them? Now, it might just be the angle between these 2 vectors cut in half, but we are not accounting for the scale of these vectors, because in cosine similarity we actually don't care about the scale, we care about the angle. So if we are scaling out the same kind of vector into unit distance or much longer distance, what does that mean for changes to the average point, or the average point between 2 vectors in the cosine similarity case? So rather than talk about averages, in the non-Euclidean case, what we do is we talk about only other points in our data. So here, instead of talking about the centroid of a cluster being the average point across all the points in the cluster, we can talk about the clusteroid, or the data point that's closest to all other points. That is, we can look at all the points in our particular cluster and identify which point here is closest to all other points. And now we have to talk, or we can talk explicitly only about the data points in our data. So here we have an example of 3 different data points. We've identified a cluster around them, and in the Euclidean case, we could identify the center of this cluster as its cluster centroid, which is just the average of these 3 points. But in the clusteroid case, or in the non-Euclidean case, our clusteroid is an actual point in our data, and it is the point that is the closest to other points in our data set. Now note the clusteroid and the centroid need not be the same, and in fact are generally not the same. But they could be. It's possible for that to be the case. Then we talked about evaluating distances between clusters, because there are a number of ways to do this. One is to evaluate distances between this summarized cluster center, or centroid or clusteroid. And we talked about other different methods for evaluating intercluster distance. And go back and look at the previous lecture for that. The last thing we talked about are stopping conditions for clustering. So in the hierarchical case, we want to understand, well, when do we stop joining or splitting our clusters? And maybe we know that from domain knowledge because we're looking at a particular case where we've somehow pre-specified the number of genres of books, or the number of political parties in a case, or the number of different kinds of galaxies that may exist, and we can impose that structure on our data by saying, well, we know that there's this many clusters available. Or maybe you do this many clusters plus 1 to handle outliers. These are all possible. Alternatively, you might pick some value of k, some clustering, based on some metric, and then measure how that metric changes as you increase or decrease k. And this is how we approached the Girvin-Newman clustering approach from the network analysis module, where we iteratively removed edges based on their betweenness centrality and tried to evaluate or find the set of edges that we removed that maximizes the modularity of this clustering. We'll talk more about ways to do this at the end of this lecture in the point assignment method. So that brings us to the second part of this module on clustering, where we're going to talk about how k-means clustering works, and then how does it identify these clusters. How does it initialize which cluster centers we use, because there's a whole set of questions that emerge when we start talking about, well, what are our initial sets of cluster centers? And then we'll continue the discussion about selecting the number of clusters, which is one of the most common things you have to do in data science or data mining, where you have some sort of unsupervised task, some sort of clustering task, and you need to evaluate or come up with some way to set the number of clusters you want. So first, let's talk about defining k-means. In general, we're making some assumption that we're dealing with Euclidean spaces and Euclidean distances. In that space, we then pick some k value that says how many clusters we want to search for, or how many clusters we want to create. We initialize these clusters in some way, either picking points from our data or randomly selecting points in this space, and use these points as our centroids for our clusters. And then we want to try and populate these clusters by evaluating or assigning points in our data set to clusters that are close to them. And then we iterate through this process, reevaluating or reassigning points to clusters and updating our clusters until we reach some convergence. So when we talk about these clusters and populating them, what we do is for every point in our data, we want to go and place that point in the cluster whose centroid is closest to that point. So this may be a very intuitive kind of approach where you just look at the different clusters you have, take the next data point you want to look at, and say, of the different clusters, which cluster is this point closest to, and we'll assign that point to that cluster. We'll do this for all points in our data set, and then we look at the resulting clusters and update the locations of our cluster centers. So when we talk about these centroids as being a summary statistic for our clusters, we need to update them based on our new set of assignments, or our new points in space. And then we go back through and reassign all points in the space again based on their closest centroid. So once we've identified the updated centroids, we throw away all of our assignments and reassign all points again by looking at their closest centroid. So it's normal for points to move back and forth or move into different clusters based on this process. And we repeat this process until we reach convergence, where we define convergence as being some stable state in our clustering assignment. That is, from one iteration to the next, points are not moving between clusters, or some threshold number, some small number of points are moving. So you could imagine you've had oscillation, where a point moves back and forth between some pair of clusters. So you can set some threshold and say as long as fewer than X points are moving back and forth between clusters, we have reached convergence. So we can show an example here of 11 different points. We'll start off by initializing a cluster using this point in blue and this point in purple as a second cluster. And now we can go through and update all of our cluster assignments by looking at which points are closest to this point in blue and which points are closest to this point in purple. Now, this initial clustering is likely not the optimal clustering, and here you can pretty much imagine that this selection of the X on the far left, this X in magenta, was probably a poorly selected initial point for our clustering. And that's totally fine, because in the next step, we will update our cluster centers, and maybe these are no longer points in our data set, and then we will reevaluate our cluster assignments, and you see things move. And we do this again, re-updating our cluster centers, and again, we reevaluate which cluster centers our points are closest to, and you can imagine this is a stable clustering for these points, and if you were to repeat this clustering process over a few more iterations, these points would not change or move between the cluster assignments that we have. So when we pick points that we'll use as our initial cluster centers, we want to pick these points such that only one point is chosen per cluster. Now this is problematic though, because if we knew how to enforce that constraint, then we would already potentially know what the clustering should be. Because we know if 2 points are in different clusters, that means we have some idea of what the cluster assignments ought to be. So this introduces a question about how do we do this? How do we pick cluster centers, these initial sets of centroids, in a reasonable or intelligent way? That's what we'll talk about now when we talk about initializing clusters for k-means. So the most naive solution, maybe given some points in space, let's just pick k points from our data at random. Where we have specified k as the number of clusters we want. We can pull points at random or extract points at random from our data set and proceed as though those are our cluster centers. Now this is actually a relatively nice kind of approach because statistically when you are pulling random points from your data set, you're likely to hit the more frequent points from your data, which means you're likely to hit the most from the data. But there are downsides to this that we'll get to in a minute, but we can visualize what this looks like. So even if we have a non-optimal initial set of clusters, so say we put these red and green centroids in the top and this blue centroid in the bottom left, when we start assigning points to clusters using these cluster centers, quickly we have a non-optimal set, but then when we update, we can see the cluster centers move, and they move pretty rapidly to the point where we end up with the expected clustering that we would want. We have 3 clearly distinct clusters here. But that's not to say that this naive solution is perfect. There are definitely opportunities for picking randomly selected points that are suboptimal or that result in poor outcomes. So what are the implications of this? What kind of errors may you run into when you've poorly selected your... The first one is slow convergence. So we're talking about having to do multiple iterations for this data, multiple iterations and passes through our data to do the cluster assignments and move our cluster centroids. If you got unlucky and you put all 3 of your points into one cluster, this could be problematic. Also, you could have an issue where the final clustering outcome is suboptimal or represents a poor clustering of your data. So these are certain pathological cases. So imagine you have this construction here where you have essentially a symmetric data set with potentially 2 or 3 clusters here. We'll say 2. So you pick 2 points at random and update your cluster assignments. What you'll see is segmented on a non-optimal axis. And actually, if you run this clustering an infinite number of times, this won't perturb, and you'll end up with what's pretty clearly a poor clustering for this particular data. So an alternative here would be to take all of your points and randomly assign them to different partitions. So you partition the data into k groups, randomly assigning points to these k groups as though you already knew what the clusterings were, and then you identify centroids from those partitions. By using these centers of these random clusters, the idea is you can move away or address this problem of having poorly selected points in your data. There's a problem here. Namely, if you take random subsets of your data, essentially what you're doing is you're sampling your data set. So even if you take k different samples of your data, what is the expected average of a given sample? We would expect the average of a sample to be close to the average of the full data. And what this means is when we take, even if we do 3 different partitions here, the means for all 3 of these different partitions are likely to be close to each other because they're all likely to be approximately close to the global mean of the full data set. So you end up with less variation in the resulting cluster centers than you do with the previous version where you randomly selected points from your data. But like I said, this helps you here because if you take these 9 points and you subdivide them into 2 partitions, you put the initial cluster centers at the centers of those partitions should be close to the global mean, you've essentially addressed this problem. So we saw that how this configuration of points can be problematic in random point assignment, that method that we discussed. Here, this is solved by this partitioning approach that puts your initial cluster centers close to the global mean. But there is a problem here. We can actually see how this problem manifests. So say we have 4 different clusters here. We have selected our k appropriately, and we partition our points into these 4 different partitions: red, green, blue, and orange. So when we extract our initial cluster centers, all of them are going to be approximately in the same place because they'll be close approximations to the global mean for the entire data set. So you have these 4 stars in the middle. A particular issue here, though, is because of the configuration that you've ended up with, where the red, green, and orange stars sort of surround the blue star, when you then update your cluster assignments, no point in your actual data set is close to the blue point or close to the blue cluster center because it's surrounded by these other points. And then you end up dropping the blue cluster altogether because there are no points that are close to it, and you end up with a suboptimal or an incorrect clustering than what you wanted. So we can introduce a better solution here by taking advantage of some intuition. If we think about the clustering process, what would we expect to be the case, or what property would we expect to be true for cluster centers after we have finished clustering? And namely, that is, all k cluster centers are likely to be far from each other. Because remember, in our definition of the clustering task, we want points that are not in the same cluster to be dissimilar, to have high distance, meaning that 2 cluster centers should also have high distance. So we want to pick points that are far from each other. And this is the premise for the k-means plus algorithm. So we start by taking a random point from our data, say this red point in the bottom left, and then when we pick our next point, we pick our next point intelligently such that it is far away. So we can scan through some sample of the points in our data set and identify the point that's furthest away in this sample from our initial point, or the current point, select that one as our next cluster center, and then proceed again, picking a third point that is far away from the previous 2 points. And we can do this for as many iterations as necessary to identify k points, and ideally we'll end up with k points that are at least far from each other. So you end up avoiding the issue of them all being close together around the global mean that we saw in the random partitioning case, and we address issues of 3 points being, or k points being, close together in the same cluster that we saw in the random point selection process at the first one. So we can visualize this pretty easily. So here we have one point that we've selected as our first cluster center. we pick a point that's far away, and we pick another point that's far away, and we see this very quickly converges into the appropriate clustering that we wanted. And even in this pathological case, or this problematic case we saw before, picking 2 points that are far away from each other is an optimal approach or strategy because we end up with the correct kind of clustering, and we do not end up with the case where we have 2 points that were on the same horizontal plane that then lead to the incorrect clustering that we saw. And in fact, there's a website that I can link to here from Neftila Harris, where you can actually visualize this process for point selection. And in fact, how you select points or initialize the k-means algorithm is a whole area of study in and of itself, and there are survey papers on appropriate methods for doing this based on different kinds of constraints and context. So how many points you have, how rapidly you need to identify these centers, and so on. This is a decent paper that summarizes this. Now the last thing we'll talk about are strategies for selecting the number of clusters. So recall from last time, we were looking at this dendrogram. What we want to do is identify when we should stop building up these clusters. When should we stop merging? That's a different kind of task than what we have for k-means. So in k-means, while we also do not know the appropriate value for k, we'll start off with explicitly having set k different clusters, and this is not a merging task. We're trying to continue until we reach some convergence, rather than continuing to merge or divide clusters. So we can see an example of issues that come up when we are trying to pick the appropriate value of k in this point configuration here, where if we start off with too few clusters, then if we're evaluating the within cluster distance for all the points to the cluster centroids, we end up with many points that are very far away from the cluster center. Now again, maybe 2 is the appropriate number you're looking for here, but from this configuration it seems unlikely, where it seems like this data may be better represented by more than 2 clusters. So alternatively, if we get this number correct, then the interpoint distance within these clusters should be, in general, small. As you'd expect in that blue cluster on the left, most of those points are close together. The red cluster on the right, again, most of those points are close together. And we still have the occasional outliers here with the top left point in the red cluster and the top left point in the yellow cluster that are far away from the cluster center. But overall, the average distance from the cluster centers to individual points in the clusters are small. So as we add more clusters to the data, or try and represent this data with more clusters, we'll see that while we are likely to reduce the average distance from cluster center to all points, there's relatively small or relatively little improvement from the 3 cluster configuration before. Right, so if you look in the limit of values of k, once k equals the number of points in your data set, the average distance within clusters is going to be 0. But clearly that's not a useful evaluation. So how do we pick the number of k here? So recall from the hierarchical clustering case, we had 2 methods when we were looking for termination conditions, where we are trying to merge or divide our clusters until we reach some threshold based on the number of k that we've specified beforehand, or through some optimization. So in the case of k-means, we can look at k, we're selecting our k value via optimization. So when we talked about increasing the number of clusters from 3 to 4 and seeing relatively little change in the average distance to our centroid, we can actually plot this, and we see that as we increase the number of k, we see a rapid decline in average distance to our centroid. But then once we hit some point, then the change in this average distance to the centroid starts to level off. As I said, in the limit, as k approaches the number of points in your data, this value will go to 0, but that's not useful. So we want to identify an appropriate value of k where we have, on average, low distance from the centroid to other points in our data set, but we want to do so without sacrificing a lot of complexity or having to go through many more passes in the data and adding more clusters to the data. And in fact, this general kind of approach where we look for this point of diminishing returns is often referred to as the elbow method, where you look for values of k where some particular metric of interest for you or quality metric of your clustering no longer improves rapidly. Now there's a third option for evaluating K, and again this depends on your task, but we've been talking about clustering in terms of characterizing clusters in our data. So we want to be able to look at data and points in our data, see what the clusters are, the general structure of this data is, because we expect these clusters to tell us something about the data. Maybe this is a dimensionality reduction case because you want to reduce the amount of data you have from your full feature set to just a variation across the different clusters that you've identified, or you're trying to do something else that is focused on understanding what the clusters mean. But that's not actually entirely necessary, because what you could be doing instead is using these clusters in some sort of downstream task. So for instance, if you're trying to use clustering for dimensionality reduction, maybe you don't know what the lower dimensions represent. You don't know what individual clusters represent, but you want to use this lower dimensionality space for some other sort of classification task for machine learning, or maybe you're trying to do compression or something along those lines. You don't actually care about what the clusters represent. You just want to use the cluster assignment information in some downstream task. So then you can optimize or select a K value that fits or results in the highest performance of your downstream task. Maybe you're looking at accuracy or F1 or precision and recall for some classification task, or correlation like Pearson's coefficient, or mean squared error if you're doing some regression. So that's a third option, but again, it depends on what you are trying to do. Now you may ask, what is the difference between this elbow method that we just introduced and stopping conditions and determination conditions we introduced in the lecture last time for hierarchical clustering? And really it's about conceptualizing what the K value means in these two spaces. So here in the hierarchical clustering case, the K value that we're trying to identify, or the metric we're trying to optimize for, tells us when we should stop merging. So specifically in the agglomerative case, where we start with n different clusters and we're going to cluster up or merge clusters up the dendrogram, there is at some point where we no longer are getting a lot of useful information and our merging should stop. In contrast, with k-means, there's no merging and we're not trying to identify some point where we should stop merging or dividing clusters. Instead, we assume that there is always some set of k clusters in our data set, and the question is about assigning points to those k clusters. And we'll only stop after convergence, so how we use the k value in these two cases is going to differ. So how we might try and optimize or identify the k values will also differ. So that closes out our discussion of clustering, where we've introduced k-means clustering, how this process identifies clusters. We've talked about initializing clusters in k-means, and we've talked about strategies for selecting the number of clusters and what that means for k-means versus hierarchical clustering. That's it. If you have any questions about clustering or supervised versus unsupervised learning, feel free to reach out via email, via Elms, or stop by office hours of mine or the TA.